All right, people, this is the day. It's the day for the fundamental theorem of algebra. You guys have been learning a lot of good stuff about complex numbers and about polynomial graphs, and now it's time for the fundamental theorem. So this is what it says. The fundamental theorem of algebra says that a polynomial of degree n, okay, so that means that they're either n factors or that if it's in standard form, that the highest exponent is n. So it could be a cubic, a quartic, whatever n might be. Has exactly n zeros. Okay, and remember the word zeros is the same as the word for roots, or we use that word for solutions or x-intercepts. We use those terms kind of interchangeably, but here we're using the term zeros. And so every polynomial of degree n has exactly n zeros. If, so here's a little conditional statement, if we have to count multiplicity, so we have to count repeated zeros, and this new thing that we talked about is complex zeros, they also have to count. So what that means is that a cubic, for instance, every cubic will have 3 zeros. Every quartic will have 4 zeros, and so on. And in particular, we saw in exercise 8 that every quadratic then should have, so because quadratic means that n is 2, means that every quadratic should have 2 zeros. Good. So there are 3 cases, though, for quadratics. You could have 2 distinct real zeros, as is shown in this graph. So if we were graphing this quadratic, we would say that the zeros are, and again here we're looking for the x-intercepts, so -5 and -1. Okay, those are 2 distinct, means they're different from each other. Real, so they're not complex, and zeros refers to the fact here that they're x-intercepts, but also to the fact that they make the y value 0. The other case is 2 identical real zeros, and if they're identical, then we just have the same one repeated twice. And so here the zeros are -3 and also -3. The third case we saw was having 2 complex conjugate zeros. Complex conjugate just means that they have the form a plus or minus bi. Okay, and remember that counts for 2. A plus bi is one of them, and a minus bi is the other one. And that happens when we don't cross the x-axis. Okay, and so if we did the math here, here the 2 complex conjugate solutions would be -3 plus or minus 2i. Okay? How did I get that? You'll have to go back and watch exercise 8. In general, notice that this fundamental theorem of algebra does not mean that a polynomial of degree n will have n x-intercepts. Okay, in fact, here we see that this quadratic does not always have 2 x-intercepts. Sometimes it has 2 x-intercepts, sometimes it has 1 x-intercept, sometimes it has none. Okay, but we can modify this if we say at most. Okay, and so a polynomial of degree n will have up to n x-intercepts if we're counting places where it crosses the x-axis. But if we're referring to zeros and we count multiplicity and complex zeros, we say it has exactly n. Let's take a look. Here are 2 examples, and these are degree 4. Okay, so both of these are degree 4. You'll notice from the end behavior that both of these are even, And they're not quadratics. They squiggle too much for being quadratics. So these are quartics, degree 4, which means that they should both have exactly 4 zeros. What I want you to do is to pause the video and try and figure out what types of zeros each of these have. All right, welcome back. So what types of zeros are we seeing here? Well, if we're looking for 4 zeros, the first thing to do would be to start counting. So you say, well, there's 1. So I'm going to write it down. So one of the zeros is -3. And here's another one. So that's another 0 at -1. And here's another one at 2. Where's the other one? So according to the fundamental theorem of algebra, we should have 4 because it has degree 4. So where is the 4th one? And here we have to keep in mind multiplicity. And because it bounces at 2, the 4th 0 is also 2. So here we have 4 real zeros. Zeros. Okay? All 4 of them are real. 2 of them are repeated, and we can see them right there on the graph. In the second example, we'll do the same thing. We'll start counting. So here we see 1. So let's see, 1, 2, 3, 4, 5, 6. So that's -6. Here's another one at -5. Uh-oh, I don't see any other x-intercepts. Well, what does that mean then about the zeros? Because if it's degree 4, again, the fundamental theorem says we should have 4 zeros. So if only 2 of them are x-intercepts, and they're not multiplicities, where are the other 2? And the answer is that the other 2 are complex. Okay? Now we can't really tell from the graph what they are, but we do know that there are 2 more. And so one way that you can sort of visualize this is by taking a look at the fact that this graph here, it kind of scoops down towards the x-axis, but doesn't really reach the x-axis, right? So if this part of the graph scooped down a little bit further, it could potentially cross 2 more times and have 2 more x-intercepts. But it doesn't, and it's this characteristic that when it kind of falls short, it scoops towards the x-axis but doesn't really reach it. That's really a sign that we have a pair, right? So this always comes in pairs, a pair of complex conjugate zeros that are not real. And so in summary here, this polynomial, this quartic, has 2 real and 2 complex zeros. Still 4, but different kinds. You try this exercise. For each of these 4 graphs, see if you can determine, first of all, the degree of each polynomial, and then see if you can list how many real and how many complex zeros each of these has. Alright, so I hope by now you're feeling pretty confident with this. As far as degree, the first 2 are quadratic, so both of these are degree 2. And the second 2 are cubic, so degree 3. How can we tell? Well, the quadratic you might be able to recognize just from experience. The cubic, you will notice, for instance, that the end behavior is odd. Okay, so the end behavior is that of an odd function. And you might also notice that each of these has 2 turning points. Okay, And you might notice that this graph has 3 x-intercepts, and while this one only has 1 x-intercept, it could potentially have up to 3 if the x-axis had been drawn at a different place. Okay, so the first step here is identifying the degree. So n equals 2 for the parabola, and n equals 3 for these cubics. That's the total number of zeros they should have. Well, in this first parabola, since I can see 2 x-intercepts, we would say that this one has 2 real zeros. Okay? Because they are x-intercepts. But the second one, I don't see any x-intercepts, so here my conclusion is 2 complex zeros. And since 2 is all that I'm looking for, that's all there is. The third graph, because I can see 3 distinct x-intercepts, we have 3 real zeros. And in the fourth graph, I can only see 1 real zero, only 1 x-intercept, and that means, once again, that there are 2 complex zeros. And again, you can see how the graph dips down here towards the x-axis. Doesn't quite reach it, but you can see that it could potentially if the graph dipped a little lower. It just doesn't. Alright, well that's all. Please come to class ready to work and bring your questions. Goodbye.